Hi, I'm Dr. J from Modern Statistics. When reading a journal article or a textbook talking about logistic regression, have you ever felt frustrated because different authors seem to interpret odds ratios differently, and how their interpretation of odds ratios are simply not straightforward and even ambiguous? And have you ever wondered what is then the correct way to interpret logistic regression output, especially about odds ratios? Or is there something better than odds ratios? The simple answer is yes. And here are the three things you'll be getting in this video. First, using a specific example in SPSS, I'll show you the common errors that most researchers make, including your textbook authors, when interpreting the odds ratios, which has become the standard way of examining the effects of individual variables in logistic regression. The goal is so that you don't make the same mistakes that others do. Second, you learn how to accurately and substantively interpret the odds ratios for both continuous and categorical variables in logistic regression. Third, you learn how to report what is known as the relative risks using conditional probability method, which offers a much more reliable, substantive, and straightforward way of interpreting the effects of each independent variable. It's really easy to calculate relative risks, and you'll wonder why most people around you do not use them. If you want to stand out among your peers when making a presentation when using logistic regression, use relative risks. And don't use odds ratio. Odds ratio is really boring, and chances are it's not even accurate as it tends to overestimate the outcome, so try not to use it. And you'll never want to depend on odds ratios ever again for your presentation after watching this video. Here I have a data set with three variables in SPSS. The first variable is named shared knowledge. We'll use this as a dependent variable for our simple logistic regression model. Participants in this survey data were asked whether they share their experience or know-how from work with other members of their organization. The response format was either yes or no, and yes is coded 1 and no is coded 0. And I have two independent variables. One is named tenure_C. It simply measures the number of years the survey participants have been with their current organization. And our second independent variable is named full-time. It measures whether they are employed full-time or part-time. Full-time is coded 1 and part-time is coded 0. Now, for the purpose of clarity, I'll run two separate simple logistic regression models, each with one independent variable. First, I'll predict whether an employee will share his or her experience or know-how with others using tenure as the independent variable. And I'll run a second simple logistic regression model using full-time as the independent variable. So I'll present the two models. Okay, let's run the simple logistic regression model. Go to Analyze, select Regression, and then select Binary Logistic. Now, here, move our dependent variable share knowledge to dependent, and move our independent variable tenure to covariates, like so. Now, click on the Options button and select the usual suspects, which is Hausman-Lamscher goodness of fit, iteration history, and confidence interval for the odds ratios. And click Continue and click OK to run the model. Now, let's look at the output. First things first, we want to see whether our model here in block 1 fits the data better than the model with no independent variable, which is in block 0. We examine the -2 log likelihood in block 1 to see if the number is smaller in block 1 than it is in block 0, which would indicate improvement from the baseline. And looking at the -2 log likelihood from block 0 to block 1, we see an improvement as the number decreased by about 18. By the way, what is this -2 log likelihood? Well, it's a bit difficult to interpret it in substantive term in plain English, but the number is basically a measure of lack of fit. The easiest way to conceptualize this is to think of it as the opposite of R-squared. We know that R-squared is the amount of variance accounted for by the model, so this minus 2 log likelihood is exactly the opposite. So, the smaller the number is in minus 2 log likelihood, the better the model fitting the data. And the bigger the number gets, the more garbage basically your model contains. Now, earlier I mentioned our model here is better than the null model with a reduction of about 18 in minus 2 log likelihood. Is that reduction of 18 big enough for us to say the model fits the data significantly better than the null model? Well, to answer that question, we go down on the output and look at the omnibus tests of model coefficients. We see that the chi-square 18.151 is significant at the p-value being less than, well, in this case, way less than 0.05, isn't it? So we therefore reject the null hypothesis that there is no difference in probability of the outcome variable as a function of the independent variable, which is tenure in our example. By the way, since there are so many people who often misinterpret what p-value actually is and how to understand it, so let me just make sure that you understand it and you understand how to interpret the p-value here. The p-value here is less than 0.001. So the probability of obtaining the observed data, if in fact the null hypothesis were true in the population, is less than 0.1%. That's right, not even 1%. If it was 5% or higher, then we can give in and say we do not have overwhelming evidence to reject the null hypothesis. But with the p-value here being less than 0.001, there is simply no chance that the null hypothesis is true, so we have to reject it. Now, what about the model summary? Unlike linear regression model, where interpreting the R-squared is an exciting ritual, in logistic regression, it's really all about the probability. How much of the variance in the outcome variable is accounted for by the model is just not as important or as exciting in logistic regression. And the fact that the two R-squared equivalents provided here are not exactly the R-squared we're looking for doesn't help it. If you must, you can say that the model explains between 2.1 and 2.9% of the variation on the outcome variable, but you rarely see authors stating that in journal articles. So that's just FYI if you must state that. Now, let's look at Hosmer-Lamshow test before we finally look at the odds ratios table. Hosmer-Lamshow test is another goodness of fit test for logistic regression model. Now here, we want this p-value here to be bigger than 0.05. The bigger the better. Small p-values mean that the model is a poor fit to the data. So if the p-value is less than 0.05, that's where we draw the line and say the model poorly fits the data. But the p-value here is above 0.05, so we have no major concern here. And we proceed to the next table, which is really the focus of our presentation. Now remember that our dependent variable measures whether or not employees share their expertise with their coworkers. Now we see that here that the odds ratio for our independent variable tenure is greater than 1 and statistically significant, which means that generally speaking, the odds of employees sharing their expertise with coworkers in their organization increase for each additional year they spend with their current organization. This is okay. It's rather dry. It's a little bit dry, but this is okay. It's a standard way of interpreting odds ratio. Now, let's get a bit more specific. The odds ratio here is exactly what? 1.032. What does that mean exactly in substantive term? And contrary to popular belief, it should not be stated like as tenure increases by 1 year, people are 1.032 times more likely to share their expertise with others. No. Don't ever do that. The odds ratio is a ratio of odds. It's not a ratio of probabilities. So you cannot and should not use phrases like 2 times more likely or 2 times less likely. You should never use probabilistic language here. Now, in order to substantively interpret these odds ratios, if you must, which is 1.032, you need to compare two individuals or two cases that differ in their tenure, say, for example, by 1 year. For example, you can say that for someone who has spent 10 years with their current organization, their odds of sharing knowledge or know-how with their coworkers are 1.032 times the odds of those who spent 9 years with their current organization. This is the correct version, if you must interpret odds ratio. But still, here's a reason why I do not like using odds ratios. And here's the reason why. We know the odds of those who spent 10 years with their current organization, which is 1.032 times the odds of those with 9 years, which is 1 year less, with their current organization. Well, what are then the odds of those with 9 years in their organization? Well, we don't know. All we know and all we can say is that their odds are 1.032 times the odds of those with 1 year less. So the odds of one group are always relative to the odds to the other group being compared. And I don't like that. Is there a better way to report the outcome where we can report findings in percentage terms? Absolutely. Now, to explain that, let's go back to the data set. What we're going to do here is to calculate the average tenure for the 25th percentile and the 75th percentiles in tenure. And we'll then calculate the conditional probability of whether or not one will share his or her expertise with other members of the organization, one based on the 25th percentile and the second based on the 75th percentile. It's really, really easy. Let me show you. First, go to Analyze and select Descriptive Statistics and select Explore. Now, move the variable tenure to a dependent list, like so. Click Statistics button and check the box for percentiles. Click Continue and click OK to run the statistics. Now, we see that the average tenure at the 25th percentile is 1 year, and the average tenure at the 75th percentile is 16.5 years. So let's calculate the conditional probability for those with 1 year with their current organization first, and for those with 16.5 years with their current organization. The formula for calculating conditional probability looks like this. Now, all the information we need to plug into this formula is provided from this table. So to calculate the conditional probability for those with 1 year in their organization, we simply plug in the regression equation, that is 0.142 is the constant, and 0.032 is the regression coefficient for the independent variable, and for tenure, we plug in 1 year and exponentiate it, and we do the same at the bottom. The only difference at the bottom is that we add 1 to it. And we do the same for those with 16.5 years with their current organization. Again, the only difference is that since we are calculating the probability of sharing expertise with others for those who spend 16.5 years with their current organization, simply we plug in 16.5 for tenure. Now let's do this in SPSS. Here we are back in the data set. Now to calculate the two conditional probabilities, we go to Transform and select Compute Variable. Then name the probability for those with 1 year, and let's just name it P1 for those with 1 year with their current organization. And plug in the values into the formula like so. And we're done. Click OK. Then we have a new variable named P1. And we find that for those who spent 1 year with their current organization, they have 54% chance of sharing their expertise with their coworkers in their organization. Now, let's do the same calculation this time for those who spent 16.5 years with their current organization. We'll name it P2 this time and plug in the values into the formula like so. And of course, we enter 16.5 this time because we want to compare the probability of tenure at 25th and 75th percentile. Click OK, and we see variable P2, right, which shows 0.66. So for those who spent 16.5 years with their current organization, they have 66% chance of sharing their knowledge or expertise with their coworkers in their organization. By the way, this is a real data, and it's interesting how people, even after spending more than 16 years in their organization, that still 34% of them will not share their knowledge with others in their organization. Interesting, isn't it? So, to summarize, those with 1 year in their current organization have 54% chance of sharing their knowledge with coworkers. And for those with 16.5 years in their current organization, they have 66% chance of sharing their knowledge with coworkers. Much more transparent and straightforward this way, rather than saying the odds are whatever times greater than the odds of another group and so on, right? Then we calculate the relative risk, which you will get simply by dividing 0.66 by 0.54, which is 1.22. Now, we can finally say it in probability terms. That is, people who have spent 16.5 years with their current organization are 1.22 times more likely. Yes, you can now say it. 1.22 times more likely to share their knowledge with their coworkers than those with 1 year in their current organization. So that was our first model. Let's run a second model this time. The independent variable is a categorical variable, full-time versus part-time. When you have a dummy variable like this, you can easily find out why odds ratios are sometimes unreliable and why they tend to exaggerate the odds. We'll find out soon enough. So, we run the logistic regression model this time using the dummy variable named full-time. And it's coded 1 for full-time and coded 0 for part-time, just to remind you. Now, the only thing we need to do differently at this point, since it's a categorical variable, is that we need to let SPSS know that this is a categorical variable. So, click the button that says Categorical and move the variable to the right. And full-time is again coded 1 and part-time is coded 0. And we'll use part-time as the reference category. And 0 comes first before 1. Doesn't it? So we don't need to change that, so just leave it as it is and click continue and click OK to run the model. Now let's look at the two most important tables here, which is the omnibus test of model coefficients, which tells us whether our model here is an improvement from the null model, and the p-value tells us that this model with the categorical independent variable is a significant improvement from the null model, the baseline model. Now, let's look at the odds ratio. We state that the odds of full-time employees sharing their knowledge with coworkers are 1.956 times the odds of part-time workers sharing their knowledge with coworkers. Again, it's a little boring, but at least it's a correct way of interpreting the odds ratio. Again, let me remind you that we don't say that full-time employees are 1.956 times more likely to share their knowledge. No, we don't do that. Again, this is an odds ratio, not a ratio of probabilities. So we should not use language like more likely or less likely. So just like we did before, let's calculate the conditional probabilities. One for each group, that is full-time workers versus part-time workers. So we plug in the values like we did before to create the conditional probability for the full-time workers. Full-time workers are coded 1, so we plug in 1 for full-time, right? And we do the same for part-time workers, and we get the conditional probabilities for full-time and part-time workers like so. So when converted to conditional probabilities, we see that full-time workers have 59% chance of sharing their knowledge with their coworkers, while part-time workers have 42% chance of sharing their knowledge with coworkers. And we calculate the relative risk by dividing 0.59 by 0.42. Then we get 1.40. So we can now say that full-time workers are 1.4 times more likely. Yes, we can now say that because this is a ratio of probabilities now. Again, full-time workers are 1.4 times more likely to share their knowledge with their coworkers than part-time workers do. Now, if you think back, what was the odds ratio for this model? The odds ratio was 1.96. But here, our relative risk says full-time workers are 1.4 times more likely to share their knowledge than part-time workers. So, my recommendation for you is that you use conditional probability and relative risk for clear and straightforward interpretation, and do not use confusing language like odds ratio and ultimately run the risk of misinterpreting your results. For those of you who are just learning about logistic regression, or for those who've used logistic regression before and for a long time, but are still confused as to just how we should read and interpret the odds ratios, you now know how and know what is ultimately a better approach than using odds ratios. I hope this video was useful for you, and if you subscribe to this channel, then I hope to see you next time. Thank you.